Kia ora and welcome back everybody. Today we're going to be talking about Cramer's rule for solving linear systems and also Cramer's rule for finding the inverse of a matrix. Now when we were learning Gaussian elimination, you may have wondered, well, this is an algorithm for solving linear systems, but wouldn't it also be nice if there was a formula that you could write down in a single line and it gave you the solution of a linear system? There is such a formula. That's what Cramer's rule gives you. In fact, this rule for solving linear systems, this was invented by or discovered by Cramer in 1750, and to do this he has to first discover the determinant. So the formula for the determinant was already known for 2x2 and 3x3 systems. He discovered the general formula that works for all matrices and detects when a matrix is invertible. That was in 1750, so already at that time there was an urgent need in science and technology for solving linear systems. Here we go. So A is going to be an n by n matrix. B is going to be the vector in Rn for the right hand side of the linear system Ax equals B, and we want to get a formula for the components of the vector x of the solution. Now I'm going to take that matrix A, it's an n by n matrix, and I'm going to partition it up by its columns. So the first column will be the vector A1, second column will be the vector A2, and so on. And I'm going to build a new matrix called AI of B, where I take that matrix A and I take the ith column and I replace it by vector B. So that's actually a bunch of new matrices. There's A1 of B, where you replace the first column by B, A2 of B, where you replace the second column by B, and so on. So with that in hand, here is Cramer's rule for the solution of linear systems. Xi, that's the ith component of the solution vector, it's the determinant of AI of B divided by the determinant of A. So it's a short compact formula, but it does involve determinants. The denominator there, determinant of A, that's the same for every component, so you just work that out once. The numerators are different for each component I, and you have to work those out for I equals 1 to n. Now we are actually going to prove Cramer's rule. It's possible to do it with all the tools that we know already, but first let's do an example. So here's a linear system. 4x1 plus 3x2 equals 10. x1 plus 2x2 equals 15. So I write down the coefficient matrices. Matrix A is 4, 3, 1, 2. The right hand side B is 10, 15. The determinant of A, that's 4 times 2 minus 1 times 3, that's 5. So here we go, Cramer's rule. x1. So I take the matrix A, I replace the first column by B, that gives me the matrix 10, 3, 15, 2. I take its determinant, I divide by the determinant of A, which is 5, I get minus 5. For the second component, x2, I go back to my original matrix A and I replace the second column of A by the vector B. I get the matrix 4, 10, 1, 15. I take its determinant, that's 60, 4 times 15 minus 1 times 10, that's 50. Divide by 5, which is the determinant of A, and you get 10. So the solution is vector x equals minus 5, 10. So for small matrices, this is quite a practical method of solving linear systems. It gives you a formula, an algebraic formula in terms of the entries in the matrix. That could be quite useful if the entries in the matrix or the right-hand side are algebraic expressions involving variables like x. Then you get a formula for the solution, which could be just what you need. So here we go. Now we're going to actually prove this formula for Cramer's rule. It's going to involve the identity matrix, which is the matrix with all zeros except for ones along the diagonal. And I'm going to take out the columns of the identity matrix. So the first column of the identity matrix, which is 1 followed by zeros, that'll be the vector E1, then the vector E2, and so on. I'm going to say that Ax equals B, so I'm assuming I've got a solution and I want to solve for x. Now the next line seems to be a little bit unmotivated, but in just a couple of lines of algebra you'll see exactly why this is what we need. We're going to take A times the ith column of the identity matrix with column I substituted for vector x. So that's A times E1 to En, except where column I has been replaced by x. Multiply through, I get A times E1, A times x, A times En. Now A times E1, that's just the first column of A, so that's A1. A times x, that's b, because ax equals b. A times en, that's an, the nth column of A. Now what is that? Well, that's just the matrix A, where column I has been replaced by B, so that's AI of B. So matrix A times II of x is equal to AI of B. That's a matrix equation, but I take that matrix equation, two matrices are equal, therefore they have the same determinant, so I'm going to take determinant of both sides. That means the determinant of matrix A times matrix big I little I of x, well, that's the determinant of a matrix product. We know from last time that the determinant of a product of matrices is the product of the determinants, so I get the determinant of A times the determinant of big I little I of x. We're getting close there because now we have the determinant of A, which we know we want in the answer. On the right hand side I just get the determinant of AI of B. Now I have to look at that term, determinant of big I little I of x. Let's work that out. Well, that's the identity matrix where column I is replaced by x, and I have to take the determinant of that matrix. Remember, that's an n by n matrix, so that could be difficult. What's the most sensible way to evaluate the determinant of that matrix? I want to expand along the ith row. Laplace expansion along the ith row, because almost all the entries there are 0. There'll only be one non-zero term, which is in the II position. That gives me minus 1 to the I plus I, that's my plus minus part, times xi, times the determinant with row I and column I crossed out. Well, that crosses out nearly everything. There's only the identity matrix left. Its determinant is 1. Altogether I get xi. Move the determinant to the other side and we get Cramer's rule. So now you might need to go back through that a couple of times to see how the logic flows and how the calculations and the determinants and so on, but that's it. That's a formula for the solution of a linear system. Now we can, as an application of Cramer's rule, we can actually get a formula for the inverse of a matrix, which is also useful, especially when the matrix has symbolic entries. So let x be the inverse of A, assuming that A is invertible, so assuming its determinant is non-zero. That means A times x is the identity matrix. I'm going to solve for the columns of this matrix big X. So I'll call the columns vector x1, vector x2 up to vector xn. And that means the row I column j entry will be xij of the matrix X. So writing as a linear system, I get A times vector xj equals vector ej. That's the jth column of the identity matrix. That's a linear system. Write down the solution using Cramer's rule. It tells you that xij is the determinant of ai, where its jth column is replaced by ej. Sorry, its ith column is replaced by ej, divided by the determinant of A. So let's write down that matrix. We need the determinant of ai of ej. Here's where you have to check the rows and column indices very carefully. I'm starting with the matrix A. I'm replacing the ith column by ej, which means it's all zeros except for a 1 in the ji position. How am I going to evaluate that determinant? Well, look at the ith column. It's almost all zeros. I should do a Laplace expansion along the ith column. What I will get is minus 1 to the j plus I times the determinant of that matrix with the row j column I position crossed out. Well, that's just cji. It's the ji cofactor of the matrix A. So I've got my formula. xij is cji divided by the determinant of A. So if I put all of those cofactors into a big matrix C, I'd have that the inverse of A is 1 over the determinant of A times the transpose of the matrix of cofactors. It's transposed because the indices are swapped around. So the row I column j position in A inverse comes from the row j column I position in the matrix of cofactors. You swap the row and column indices. Okay. Let's do an example. Let's use Cramer's rule to find the inverse of this matrix 2, 0, negative 1, 0, 1, 1, 1, negative 1, 0. First I need the determinant. I'll do that by expanding along the first row. That comes out to be determinant equal to 3. And now I'll need all 9 cofactors. I need the cofactor of every element. So C11, cross out the first row and column. That gives me the matrix 1, 1, minus 1, 0. Take the determinant, I get 1. C12, the 1, 2 cofactor. Cross out the first row and second column. Take the determinant, introduce a minus sign, because remember the plus minus checkerboard pattern of plus and minus signs enters into the cofactors. I get C12 is equal to 1. So I continue in this way. I'll let you check the details. I work out all the cofactors. I get the matrix of cofactors. It's 1, 1, negative 1, 1, 1, 2, 1, negative 1, 2. And then I take the transpose of that matrix, giving me A inverse is a third, that's the 1 over ZA part, times 1, 1, 1, 1, 1, negative 2, negative 1, 2, 2. Now, that was just an example. In that case, it would have been a similar amount of work to find A inverse using the row reduction method, but it's still very convenient to have an algebraic formula for the inverse that you can use if you want to do some algebra with it, like manipulate it for some other application.